Hi everyone. Today is, or rather this week, is POPL week. So POPL stands for Principles of Programming Languages, and it's one of the major conferences in the calendar year. And it just so happens to be in Philadelphia, and it's happening in person despite coronavirus. So this is a very fun week. So I've been there this week, and what's wonderful about these conferences is just the amount of trading of ideas and different directions to go for the future, and it's just fantastic. One of the conversations I had this week was around deferred type errors. I want to share that with you, and then toward the end of the video, I'll connect this up with maybe a future research idea. But I realized there's no video out there that I've made yet about deferred type errors. So I want to just sort of introduce this GHC feature. It's really quite useful, and it's, I think, quite clever. Fair disclosure, I had nothing to do with this idea when it came about, but I really do like it. So here's a motivating example. So let's say we have some tree type. So we might have leaf and, let's make it polymorphic. Why not? So we have a leaf, and then we have a node, and then the node has a left child, and then some data, and then a right child. That's our tree type. And now I want to have something that does an in-order traversal. So we're going to have an in-order, and on a leaf, it's going to return the leaf, and then on the nodes, we have left, and then X, and then right, and it's going to be in order of left, append X, append in order of right. Okay, that's right, that's what I wanted. Okay, because this was just going to be that one element in the middle. And sure enough, I get an error here. So I point at the error, and occurs check cannot construct the infinite type. Well, okay, fine. But I still want to load this up. So let me load this into GHCI here. So I load that up, and it's loading, and I don't know why this is taking so long. It shouldn't. This is very strange. There we go. And we get my type error, but actually I'm still just trying to understand what's going on here, maybe. And so I want to know what the type of leaf and node is. So I'm going to just say T leaf. Well, there's no leaf constructor in scope. Well, what about node? There's no node constructor in scope. And that's because my file didn't load. And that's because it had a type error down here. But actually, these queries that I'm making here, they make perfect sense. Even if I have a type error down here. So maybe I can't call my in-order function. But I still want to be able to do some queries about a file. Now, this is a very small Haskell file that I've written here. Imagine I've written 2,000 lines. If I have one type error, that means I can make no queries about the file? That doesn't sound so good. So that's why GHC supports deferred type errors. So I'm going to turn it on in the file, because if I turn it on in GHCI, then I won't be able to turn it off again easily. So if we turn on F, deferred type errors, and this is a compiler flag. Oh, not language. No. Options GHC. Excuse me. I don't know where that came from. Options GHC fingers. So if I say options GHC, now that means that when this file gets compiled, it will activate deferred type errors. So now if I try to reload down here, have I done something strange? Unknown flag, F deferred type errors. Oh, it's not defer. The feature is deferred type errors, but we're asking GHC to defer the type errors. I'm surprised it didn't suggest that. Let's try this. Hopefully that will work. Hooray. Okay, so what has happened here is now, in what was previously an error, is now a warning. Because it's saying there's still a problem here. We still want to know about the problem, but it's actually a warning, not a proper error. And so my file is loaded. And I can do things like I can say, what's leaf? And it will tell me. And I can say, what's node? And it will tell me. So that's very good. If I try to call in order, let's see what happens. So if I call in order just on a leaf 5, let's say, then I get a runtime error. Right? It's not very clear here that this is a runtime error. If I made a main program, we would see this is really a runtime error. And that's because my function here, it doesn't actually work. So we can't call in order, but we can still load the file. That's what deferred type errors are. And actually, that's what powers this feature in the Haskell language server. So even if I turn this off, right, here we see that the Haskell language server is telling me what the type of in order is. How does it know that? Well, it knows that because it actually loads the file internally with deferred type errors on, and then it can query the type. So sometimes we can see this fact. So every now and then, the fact that it's using deferred type errors leaks, right? HLS shouldn't really be doing this, right? We probably don't want to be printing that out here because this is more of an implementation detail. It just happens to be the way that HLS interacts with GHC to get the information that we want. I'm hoping in the future maybe there can be sort of a tighter connection between HLS and GHC such that it doesn't have to use this, essentially a workaround. So that's deferred type errors. It allows you to ignore most type errors, not all of them. I don't want to get into details about which ones are and which ones aren't. Allows you to turn most type errors into warnings, but that when you run the function, you get the error then. So I want to explore, that's the motivation. Let's explore exactly what this means. So the first thing that it means is it does not mean that suddenly Haskell is a dynamically typed language. So let me show you something that makes perfectly good sense in a dynamically typed language. And that might be, to say 5 equals let list equal, 2 hello 5 or 3 in, list access the 0th element plus list access the element number 2, and I don't know about precedence of all of these operators, and I don't know why I put plus plus there. It must be late at night at a conference week. So here, let's see, we have all of this stuff, and of course there are errors, right? I've made a list here with some numbers and then a string in the middle of it, and actually the error here that we get is a little bit confusing. It says no instance for num list of car. This actually makes sense, right? Because 2 and 3 are overloaded numbers, and so it's saying, well, maybe you want your overloaded numbers to be strings, but that only makes sense if a string is a number. And then over here, let's see, again, no instance for all of this. All of this stuff is giving us trouble. That said, in a dynamically typed language, like in Python, we could write code equivalent to this, and it would work, and it would actually compute to 5. So let's load this into GHCI here. Of course, we're going to get that type error. So let's turn on deferred type errors, and we will load. And now it's just a warning. And if I try to evaluate 5, then I get this error. And that's because I said it's not a dynamically typed language. Instead, it's still doing type checking, but what GHC does as it's doing type checking is it's trying to say that one thing is equal to another. That's one of its big operations, to say that this type equals that type. Although actually here, this is not one of those errors. This is this num car thing. So let me tailor my explanation to the actual error that we're seeing. Whenever we have a number here, GHC needs to supply how to sort of convert that number as an integer into whatever type it is that we're looking at. So in this case, a string. It won't be able to do that, and so GHC inserts just a little, what's called a dictionary. A dictionary says how to actually implement methods in a class. The dictionary that it inserts, when you evaluate that dictionary, throws this exception. That's maybe a little bit confusing, so let me simplify the case a little, and let's forget about overloaded numbers. So if I put these type annotations, so now I'm forcing these to be int, we're going to get a different error. Couldn't match expected type int with actual type car. So let's reload this, again with deferred type error, so it's a warning, the load succeeded, and I evaluate 5, and now we see could not match expected type int with actual type car. What's going on here is that it sees that there's this int, and then there's this list, this string, not list of cars, I'll just call it a string. And GHC says, okay, well, so we need list of car to be the same as the type int. What it will do is it will create a proof that, in fact, string and int are the same type, except that the proof that it uses when you evaluate that proof, prints out this message and aborts your program. And so it's almost like we have something like this. But we need a type for bad proof. I guess it would be the other way around, wouldn't it? Because we're going from string to int. And then here, so this won't quite work. You can't use a type like this. This is more for sort of illustrative purposes, in that GHC will invent this proof saying that string is really int. And once it has a proof that string is int, we can take hello and cast it by that proof. And when we do that, or we can cast it by that proof, and then this expression here, casted by the proof, would actually have type int. We'd have our nice list that just has ints, and we'd be able to then access it. So that's how this deferred type errors works under the hood, and then it means that when we try to evaluate certain parts of the expression, we're going to get this error. Now it doesn't always, the error isn't always going to occur. So like if, let's say, instead of trying to evaluate it like this, if we just maybe took the length of the list, does that work? It might just work. Let's comment out, let's comment out the pieces that were just for illustration. So now we have this strange list here, but we're only finding its length. Maybe GHC will allow us to do that. No, it doesn't. I think that's because this proof is actually a strict binding, the way that GHC does it. And so when we sort of get into this let, it will immediately evaluate this, and then we get the error. So we'll only get the error if we start to run 5, not if we sort of just use other functions in our program, right? If I write somewhere else 6 equals 6, and I load this, then I can certainly evaluate. Oh. What? That's strange. I don't know what's going on. I think it has to do with defaulting, I'm sure. But I think this is a bug. Yay, I get to report another bug. So let's ignore that, and instead I'm just going to give 6 a type signature to avoid that problem. And then now, 6 really has type 6. Though that's very interesting. That's an interesting kind. That'll be a fun bug. So here, again, the point of deferred type errors is it allows us to load our program, make queries against it, even run parts of it, while still protecting us from the bad code. So I said at the beginning of the video that this connects to maybe some future research ideas. So one problem when thinking about type errors is, well, when thinking about errors in general is we've all had the experience, once you program for a little bit, is that you're working on a file and it has a bunch of errors, and you fix the errors one by one, and then there's just one error left, and you fix that error, and you load, and now you have 10 new errors. And the reason for that is that sometimes you have one error that sort of masks a whole bunch of others. It would be nice to know, when we go from that one error to the 10 errors, that actually things have improved, right? Naively, it looks like I went from one error to 10 errors, that's bad. But actually, once you've gained experience programming, you know that's not necessarily bad. Well, what if instead of counting the number of errors, what if somehow we gave an indication for how much of the program, how much of your file is erroneous? With these deferred type errors, we could think of saying that any part of your program that you can't evaluate because it would trigger one of these errors at runtime, that's the area of the program that has type errors. And so if you make that region of your program smaller, then we've made progress. Even if we take one type error that says a whole big function is broken, and now we maybe fix the big function, but now there's some smaller definitions within that function that are broken, that's forward progress. It might turn one error into 10. But actually, the amount of code that's sort of covered by the error, I think, would decrease in that case. So that was sort of the little locus of the idea. That was a conversation I had with Garrett Morris, with whom I've written a few papers. So maybe there's some future in that. I don't know. It would be nice, for example, to have some automated way of sort of monitoring students, say, with their consent, of course, that says, are they making forward progress? Are they not making forward progress? And then that way we can actually even use that information to look at error messages and see, well, are these good error messages? Are these bad error messages? I don't know. There's still a lot more work to be done in that direction, but it was kind of a fun thought, and it made me think of deferred type errors, which seemed to be a good thing to explain in a video like this. Thanks very much for watching. Hope this has been interesting. Bye.